Welcome back. In this lecture, I present to you the state space search. The objective here is for you to have a good mastering of the various concepts related to search and also the categories of the search control strategies. So, introduction. What is search? The word search refers to the search for a solution in a problem space. Is it okay? Search for solution. A solution is what? It is a sequence of state changes from the initial state to the goal state. Okay. Now here the problem space is what? It is just the set of states. Is it okay? Because a problem is defined by the various states of the problem, and then the solution should be the sequence of state changes. It means the sequence of operators. Example, in the an example in this missionaries and cannibal problem, the state is what? It is the number of missionaries and cannibals on both sides of the river and the position of the boat. So that is a state. And then a state change is what? It is a trip from one side to the other side. Another example, in this 3x3 puzzle game, a state is the positions of the various tiles. Is it okay? And then a state change is what? It is a move, either up, left, or right. And then the initial state is the start state or the current state. So in this problem, this is the initial state, and then the goal state. This is it. So the tiles should be arranged in this manner. Okay. Now in this other problem, the initial state is 3 missionaries and 3 cannibals on this side, and then the position of the boat. See? Now what is the goal state? The 3 missionaries and the 3 cannibals should be on this side with the boat. So fine. Now the search proceeds with a specific control strategy. So we have what is called a control strategy. Now, what is the strategy? A strategy is defined by picking the order in which the nodes expand. Is it okay? What is the meaning? In this problem, for example, this is the initial state. From this initial state, there are different states where we can go to. Like, you see, one of the operations that can be performed here is the up. That is to move this one up. Then you have left, you have right. So if you take the first operation up, you give us one child of this node. When you take left, you give another child. When you take right, you give another child. So the strategy defines the order in which we expand the children of this node, and recursively, because each child will be expanded and we give its own children. So what is the order in which we should expand the children of each node? So that is what is called the strategy. Is it okay? Fine. So a strategy is defined by picking the order in which the nodes expand. Search usually results from a lack of knowledge. So why do we search? Just because we don't have the knowledge, we don't know exactly how the solution should be obtained. Is it okay? So in this problem, for example, from this state, we don't know how to get to the goal state. So that is why we should search for the solution, because we don't know the solution. Is it clear? Fine. So search is the systematic examination of states to find path from the start or the root state to the goal state. So in the search, we examine the various states to find the goal state, because from the initial state we go through the children, and then we examine all the states one after the other to find the goal state. So that is the search. Search deals with finding nodes having certain properties in a graph that represent search space. It's okay, finding nodes having certain properties. For example, in this problem, the search will find the node or the state where the board game as it is, like this, and then with the tiles arranged in this manner: 1 2 3 4 5 6 7 8, and then the empty cell in the middle. So the search will examine the state to find the state where the tiles are arranged in this manner. Is it okay? Fine. Search methods explore the search space intelligently, evaluating possibilities without investigating every single possibility. So what is the search space? It is just the set of states. Is it okay? So what do? We explore the search space. We use a specific method called the control strategy. Is it okay? Fine. So we evaluate all the possibilities. All the possibilities. Now let's move to states. So what is a state? A state is a representation of elements in a given moment. In this missionaries and cannibal problem, what are the elements? You have the missionaries, the cannibals, and the boat. So their representation at any time is what is called the state. For example, here a state is what? The number of missionaries, the number of cannibals, and the position, the number of missionaries and the number of cannibals on both sides of the river, and also the position of the boat. Now in this other problem, a state is what? It is the arrangement of the tiles on the board, because the elements are, you have the board and the tiles. So now the state is the arrangement of the tiles on the board. Fine. Now, a problem is defined by its elements and their relationships. Is it okay? So the elements here, we have the missionaries, cannibals, and the boat. So their relationships. So that is the problem. At each instant of a problem, the elements have specific descriptors and relations. The descriptor indicates how to select elements. If we go back to this problem, for example, we know that we have 4 operators: up, down, left, and right. But how do we select a state from this one? When the empty space is at this position, we know that the down operation cannot be applied. That is the descriptor. We cannot use the down operation, so you cannot move down. You can only move up. Left and right. But when you are here, when the empty space is in the middle, you can move up, down, left, right. But if it is at the corner, for example, this corner, top left corner, we can only use the down and the right operators. So those are the descriptors. Now, among all possible states, there are 2 special states. So we have the initial state, that is the start point, the final state, that is the goal. In this problem, this is our initial state, that is the current state, and then this is the desired state, the goal state. Fine. Now we move to state change or successor function. A successor function is needed for state change. So to change from one state to another, we need a successor function. So that is what is called a state change. To change from one state to another, to move one state to the other state. Fine. Successor function. It is a description of possible actions. It means set of operators. In this board game, the actions are up, down, left, and right. In this problem, the actions are the trips. In each trip, we carry 2 passengers. Is it okay? Can be 2 missionaries, can be 2 cannibals, or can be 1 missionary and 1 cannibal. We can even carry 1 passenger. It can be 1 missionary or 1 cannibal or 0, but the maximum number of passengers should be 2 to cross from one side to another, either from left to right or from right to left. So these are the actions. So a successor function is a transformation function on a state representation. So a function that transforms a state to the other state. Is it okay? So it converts a state into another state. It defines a relation of accessibility among states. Accessibility. So from this state, for example, what are the states that are accessible? The state directly accessible from this one are when we apply the up action. So this 6 we go down. So that is, we obtain one state that is accessible directly from this one. When we also apply the left function, we obtain 1, 3, 4, 2, 5, 7, empty, 8, 6. So that is another state that is accessible directly from this one. So that is it, the accessibility. It represents the conditions of applicability of a state and corresponding transformation function. So here, when the empty space is at this position, there are only 3 operators that can be used. Okay, so that is, it means that from this initial state, the states that are directly accessible are only 3. So that is the applicability of the state. Operators consist of preconditions and insertions. So it means that each operator is a precondition and an instruction. The precondition provides partial description of the state of the world that must be true in order to perform the action. For example, to perform the down action in this problem, the empty space should be either on the first line or on the second line. You see, if the empty space is on the third line, on the third row, you cannot apply the down action. Is it okay? So that is the precondition. So to apply the down action, make sure that the empty space is either on the first row or on the second row. Fine. And then, what is the insertion? It tells the user how to create the next state. Operators should be as general as possible so as to reduce their numbers. Now, state space or search space. So what is the state space? A state space is a set of all states reachable from the initial state. So from this initial state, what are the states that are reachable, that are accessible? So that is what is called the state space, or also called the search space, the space in which we search for the solution, this space in which we should search for the solution. So that is the state space. Okay. Fine. A state space forms a graph or a map in which the nodes are states and the arcs between the nodes are actions or operators. So the state space is represented as a graph, and we know what a graph is: set of nodes linked by the axis. Is it okay? So that is the second lecture on data structures. Fine. In a state space, a path is a sequence of states connected by a sequence of actions. We know that a path in a graph is a set of nodes linked by arcs from the initial node to the final node. So in this state space, such a path is what? It is a sequence of states connected by a sequence of actions. So the problem here can be, what is the path from this initial state to this? So from this initial state, okay, what is the very first state that is reachable from this one? It means that what is the state that is directly connected to this? After that, so we obtain a child of this. Now, which state is directly accessible from that child? We obtain another state, and you see, gradually we form a path to this goal state. So that is a path. Fine. The solution to a problem is a sequence of arcs from initial state to goal state. So we obtain a solution by what? So it is just a sequence of arcs. The arcs are what? The arcs are the actions or the operators that transform the state to other states. So a solution is just the sequence of actions. Here, for example, it is a sequence of moves to transform this initial state to the goal state. Or in this problem, to move these missionaries and cannibals from this side to the other side of the river. Fine. Now, what is the structure of that state space? As we said, the state space is a graph or a tree. It's okay, it is a graph. Now, the search process explores the state space by visiting the nodes to find the goal state. Okay. Now, in the worst case, the search explores all possible paths between the initial state and the goal state. That is in the worst case. In the worst case. Now, the solution to the problem. In the state space, a solution is a path from the initial state to the goal state. It's okay. It means that a sequence of actions to transform the initial state to the goal state. A solution cost function assigns a metric cost to each path. The metric cost to each path. It also gives the cost of applying the operators to the state. So when you have a solution, you can then calculate the cost of that solution. For example, in this problem, the cost of the solution can be the number of moves to reach the goal state. Is it okay? And a good solution is where you have the minimum number of moves. In this other problem, the cost of a solution is the number of trips, and a good solution should have the minimum number of trips. Is it okay? Fine. A solution quality is measured by the path cost function, and an optimal solution has the lowest path cost among all possible solutions. Is it okay? The solution can be any or optimal. So in this problem, the solution can be any solution, means that any sequence of trips, or the solution can be the optimal solution, that is the minimum number of trips. The importance of cost depends on the problem and the type of solution asked. Fine. Now, problem description. How do we describe a problem? A problem consists of the description of the current state of the world, called the initial state. So to describe the problem, you should give the initial state. In this problem, the initial state is that you have 3 missionaries and 3 cannibals on this site, and the position of the boat. So the boat is here. So that is the initial state. So the actions. So you should also describe the actions. That is, we define the successor function, the various operators that can transform states to other states. Fine. The desired state, that is the goal state, what we want. The state space, that is the total number of states. But that state space can be defined explicitly or implicitly. It means that we can represent the graph explicitly by drawing all the nodes and all the arcs, or it can just be implicit. Implicit means that here we just know that, okay, so we have this first state, this initial state, this one. The other nodes are not represented, but we know how to get to those nodes. It is just in our mind. For example, in my mind, I know that if I apply the up operation to this node, I will obtain this arrangement: 1, 3, 4, 2, 5, 6, 7, 8, and empty. So it is just in your mind. The graph is represented in your mind, not explicitly. So fine. A state space should describe everything that is needed to solve a problem, and nothing that is not needed to solve the problem. Okay? It should represent only what we need to solve that problem. Now, problem solving. It is finding a solution. It means find an ordered sequence of operators that transform the current state into the goal state. That is how we solve the problem, by finding the ordered sequence of operators to transform the initial state to the goal state. So that is what we call the search process, finding the solution. finding the ordered sequence of operators. Fine. Now there are some issues in the design of search programs. Each search process can be considered to be a tree traversal or graph traversal. So that is tree traversal, graph traversal. What is the meaning? It means visiting all the nodes in a graph or in a tree, following a specific strategy. The object of the search is to find a path from the initial state to the goal state using a tree or a graph represented either explicitly or implicitly. The nodes generated might be so many, and in practice, many of the nodes will not be needed. The secret here is generate only the nodes that are likely to be useful. Is it okay? So that is the secret. To generate only the nodes that are useful, rather than having a precise tree. That is why you should instead have but the implicit representation of the graph or the tree, rather than explicitly represent the entire tree. Is it okay? You should have in your mind that we talk about the efficiency or the performance of an algorithm measured in terms of the time and the space consumption. If you represent the entire tree or the entire graph, it may take a lot of space in memory, but when it is represented implicitly as a man, you generate only the nodes that are useful. So as a man, you gain in memory space. The rules are used to represent the tree implicitly and only to create nodes explicitly if they are actually to be of use. So these are some issues. The tree can be searched forward from the initial node to the goal node, or backward from the goal state to the initial state. So that is one issue. You have to decide whether you should perform the forward search or the backward search. Now, to select applicable rules, it is critical to have an efficient procedure for matching rules against states. How to represent each node of the search process. So that is another issue. So which data structure should be used to represent the node? Here, for example, a node. Should we use a two-dimensional array? Should we use a record? So which data structure should be used? So that is another issue. Fine. So these are the various concepts related to the state space search. Now we move to the search control strategies. The search is a process of exploring a tree or graph either in its entirety or until the goal node is found. The search starts at a given node and expands its neighboring node using a specific control strategy. The control strategy gives the order in which the nodes expand. Generally, there are two categories of such control strategies. What are the two categories? You have uninformed search and informed search. So these are the two categories: uninformed search and informed search. So what is the difference between the two? Fine. Uninformed search is a class of general purpose search algorithms which operate in brute force way. That is the exhaustive search. Is it okay? Uninformed search algorithms do not have additional information about states or search space other than how to traverse the tree or the graph. That is why it is called the blind search. Is it okay? Blind search. So, don't have any additional knowledge about the search space. Assignment. Okay. You can traverse the entire tree or the entire graph to search for the goal state. Now, there are various types of uninformed search algorithms, like the breadth first search, the depth first search, the depth limited search, the iterative deepening depth first search, the uniform cost search, the bidirectional search. So these are the uninformed search control strategies, or the blind search algorithms. So they will be explained in the subsequent lectures. Now, what is informed search? Informed search algorithm contains an array of knowledge such as how far we are from the goal. Is it okay? Or how to reach the goal. This knowledge helps agents to explore less to the search space and find more efficiently the goal node. So that is the difference. So in the informed search, you have additional information on how to get to the goal. So it is different from the blind search, where you don't have any information. The only thing you know is your search control strategy. But in this informed search, you have the search control strategy, but you also have the knowledge on how to get to the goal. As well, man, you see, the search can be very efficient. So it is a kind of intelligent search. Fine. The informed search is more useful for large search space. It uses heuristic. So we have what is called the heuristic function. Hn. N is the current node, and then H is the heuristic function. So this function can give the cost to reach the goal, or can tell us how to get to the goal. So this heuristic is the estimate or the estimated cost from the current node to the goal state. Is it okay? So that is why this informed search is called the heuristic search. So more about the heuristic function. So it is a function used in informed search, and it finds the most promising path. It means that from a state, this current state, the heuristic function will tell us which node we should expand, which node is the most promising node to reach the goal faster. Is it okay? It takes the current state of the agent as its input and produces the estimate of how close agent is from the goal. Fine. The heuristic method, however, might not always give the best solution, but it guarantees to find a good solution in a reasonable time. Why? Because it tells us what should be the most promising node or the most promising path to reach the goal. So it guarantees to find a good solution in a reasonable time. Fine. So it estimates how close a state is to the goal. It is represented by this Hn, and it calculates the cost of an optimal path between the pair of states. Means that from this state to this one, the heuristic function will tell us what should be the optimal path. Is it okay? Fine. The value of the heuristic function is always positive, so it is a positive function. And then the admissibility of the heuristic function is given as the heuristic function. It is less than or equal to h star. What is this? This quantity is the estimated cost to reach the goal. It means that the heuristic value should be less than or equal to the estimated value. Now, some informed search algorithms. You have the greedy best first search, the A star search. Now, in the subsequent lectures, we will give the detailed explanations about the various search control strategies, either on informed search control strategies like the breadth first search, the depth first search, the depth limited search, the uniform cost search, the bidirectional search, and so on, and also the informed search like the greedy best first search, the A star search, and their applications. Thanks for your kind attention.